Hello and welcome. This is lecture number 3 in Units and Measurement chapter. In the previous lectures, we have learned about the system of units like SI, CGS and FPS. We have learned base quantities in different units. We have learned about factors to represent a very large and very small quantities. We have learned about measurement standards for length, mass and time. We have learned about parallax method for measuring large distances. We have learned about accuracy and precision, and we have learned about errors in measurement. Now the key objectives of this lecture are learning significant digits and learning about dimensional analysis. Significant digits includes rules for determining significant digits, rules for performing arithmetic operations on numbers with significant digits, and order of magnitude. Dimensional analysis includes knowing dimensions of base quantities, representing derived quantities in terms of dimensions of base quantities, and determining relation between physical quantities. Okay, what are significant digits? We know that every physical quantity is measured in numbers. Therefore, significant digits of a measurement includes all digits that are reliably known plus the first digit that is uncertain. For example, if a length of a certain object is represented as 2.148 meters, the digits 214 are reliably known and digit 8 is uncertain. Therefore, the significant digits of this measurement are 4 and they are 2148. A change in unit does not change the number of significant digits. Now, what are the rules for determining significant digits? All non-zero digits are significant. All the zeros between two non-zero digits are significant no matter where the decimal point is located. If the number is less than 1, the zeros between the decimal point and the first non-zero digit are not significant. Thus, in number 0.0024, zeros between point and 2 are not significant. The terminal or trailing zeros in a number without decimal point are not significant. Thus, in number 1,23,000, the trailing zeros are not significant. The trailing zeros in a number with a decimal point are significant. Thus, in 2.5000, the trailing zeros are significant because they signify precision of the measurement. Thus, in the light of the preceding rules, in this number, zeros between decimal and the first non-zero digit are not significant. Zeros after the last non-zero digit are significant. Therefore, we have four significant digits that are 5, 1, 0 and 0. Similarly, in this number 0002108.0500, the initial three zeros are not significant. The zeros in between are significant and trailing zeros after the decimal place are significant. Thus, in this number, we have 8 significant digits. Now, order of magnitude. Any number can be represented in scientific notation as a times 10 to the power m, where a is between 1 and 10 and it is called base quantity. M is called the order of the magnitude. Thus, the number of significant digits does not change while writing in scientific notation. All zeros appearing in the base number of a scientific notation are significant. Thus, in number 2.50 10 to the power 5, this number has 3 significant digits 250. Now, when arithmetic operations between significant figures are needed, there are certain rules that should be followed. While adding or subtracting two numbers, the number of decimal places retained is a smaller of the two In multiplication or division, the number of significant digits retained shall be smaller of the two. Other digits shall be rounded off. As we have seen in the previous slide, for performing arithmetic operations between significant numbers, rounding off of some of the digits are required. So what are the rules for rounding off? Suppose that we have a number 2.347 to be rounded off to two decimal places. The digit to be rounded off is greater than 5, therefore the preceding digit is incremented by 1. So the number 2.347 becomes 2.35. If the digit to be rounded off is less than 5, the preceding digit is left unchanged, therefore 2.343 becomes 2.34. If the digit to be rounded off is 5, we check whether the previous digit is even or odd. If it is even, it is left unchanged, and if it is odd, it is incremented by 1. Therefore 2.345 becomes 2.34 and 2.335 also becomes 2.34. Therefore the rules for rounding off can be stated as follows. If the insignificant digits to be dropped is less than 5, the preceding digit is left unchanged, and if the insignificant digit to be dropped is greater than 5, the preceding digit is increased by 1. When the insignificant digit to be dropped is 5 and the preceding digit is even, it is left unchanged. If the preceding digit is odd, it is raised by 1. Now we move to the last topic of this chapter, that is called the dimensional analysis. Now what are the dimensions of physical quantities? The units of all derived physical quantities can be expressed in terms of units of the base quantities. In dimensional analysis, these base quantities or units are denoted within square brackets. Thus, for mass, dimension is written as m within square brackets. For length, it is written as L. For time, it is written as T. For thermodynamic temperature, it is written as K. For electric current, it is written as A. For luminous intensity, it is written as CD for candela, and for amount of substance, it is written as MOL within square brackets. The dimension of the physical quantity is the power to which the base quantities are raised to represent that quantity. In this example, we want to obtain the dimensions of the force, which is equal to mass times the acceleration. The acceleration is written as length over time square. Therefore, the dimension of force is m to the power 1 for mass, L to the power 1 for length, and T to the power minus 2 for time. This table shows dimensions of some physical quantities. Volume is L cube, velocity is L t to the power minus 1, acceleration is L t to the power minus 2, force is m L t to the power minus 2, density is m L to the power minus 3 t to the power 0, and energy or work is m L square t to the power minus 2. Dimensional analysis can sometimes be used for finding relation between physical quantities. We can understand it better by taking an example. The distance s traveled by an object starting from time t is equal to 0 is a function of the acceleration and time t. We want to find the form of this relation using dimensional analysis. So we are given that s is equal to k times a to the power x times t to the power y. K is a dimensionless constant. Using dimensions for s, we write m to the power 0 L t to the power 0. Dimensions for a is m to the power 0 L t to the power minus 2, and dimensions for t is m to the power 0 L to the power 0 t. Putting these dimensions in this equation, we get this equation. and grouping the same dimensions together, we get m to the power 0, l to the power 1, t to the power 0 is equal to m to the power 0, l to the power x, t to the power minus 2x plus y. And comparing the power of base dimensions, we get x is equal to minus 1 and minus 2x plus y is equal to 0. Therefore, we get x is equal to 1, y is equal to 2, and for putting these values in this relation, we get s is equal to kat square. To summarize, in this lecture we have learned about significant digits, rule for determining significant digits, order of magnitude, performing arithmetic operations of numbers with significant digits, and rounding off. In dimensional analysis, we have learned dimension of derived quantities, and we have learned how to determine relation between physical quantities. In next lecture, we will take some problems and their solutions on this chapter.